This should be our final lesson in our tissues unit, which includes chapter 5 of our book. We have gone over all 4 of the body tissue types and how all 50 trillion of our cells are going to be classified in one of these 4 types of tissues. Either it's muscular, connective, nervous, and epithelial. And so a tissue is these cells that are coming together with a common goal or function. Our organs are going to be 2 or more types of tissues that form a discrete structure, right? And all of our 11 body systems are made up of these 4 tissue types. So we're going to talk about the tissue structure as a whole instead of the different types. Some of the things that we'll be discussing are the structures that actually hold these cells and tissues together, how tissues develop, and the types of tissue growth. So we'll talk a little bit about stem cells, and then how tissue is repaired. When it comes to cellular junctions, think of like an interstate junction. It's where 2 or more interstates meet. So cellular junctions are going to be connections between 2 cells. Most cells are anchored to each other or to their matrix. And these cells communicate with one another. They release chemicals and actually communicate to maintain the tissue. So if the tissue is damaged, they're communicating, letting those stem cells know, hey, we've got some damage here. We're going to need to replace these dead cells now. It's also going to allow them to communicate to resist mechanical stresses. For example, in the bones, we can build more dense and stronger bones in response to exercise. And these cellular junctions are also going to control what moves through the gaps and between the cells. We have to control where the molecules go so our cells can stay in homeostasis. Tight junctions are zipper-like linkage that interlocks 2 adjacent cells. So what is anchoring them together are transmembrane cell adhesion proteins. I have some pictures coming up, don't worry. This encircles an epithelial cell near the apical or free surface. They also join epithelial cells with neighboring cells. And by this interlocking link, it will actually seal off intercellular space, making it really difficult or almost impossible for substance to pass through it and go in between those 2 cells. So for example, in your stomach has cells that release hydrochloric acid. Well, if that gastric digestive juice could seep in between the epithelial cells, it would end up going down to the underlying connective tissue and destroy it. That connective tissue cannot withstand a pH of 2. It's literally an acid that would just burn through that underlying connective tissue. So tight junctions in the stomach and even in the intestines will prevent any digestive juices from getting in between the epithelial cells and causing damage. Then we have structures called desmosomes. These are patches that hold the cells together, kind of like in a baby, how they have those onesies with those little snaps that clasp together. Or one of the like old Adidas style tearaway pants, they click together with a button. so like a little clothing snap. These keep cells from being pulled apart, and it helps them resist mechanical stresses. So typically there's going to be a hook or a J-shaped type of protein that actually comes from the cytoskeleton of the cell. We see these a lot in the epidermis and in other epithelia tissues. There are half desmosomes that will anchor to the basal cells of an epithelium and connect it to the underlying basement membrane. So that way the epithelium cannot just easily peel away from the underlying tissue. And why our skin doesn't just, the epidermis just doesn't slide off of the dermis. Those are called hemidesmosomes. I was thinking of like a Hemi, the car. They're really tough. Hemidesmosomes. And the cells need to communicate. And so there are these communicating junctions or channels between the cells that are formed by like these ring-like proteins called connexin. And those are called gap junctions. And so what makes up this connexin are 6 transmembrane proteins. Remember, trans means across. So they're these proteins that go across the membrane, and they're arranged in segments of these like around water-filled channels. And this is going to allow nutrients or ions to be able to pass between cells without going through that extracellular space. These structures are very important in our cardiac and our smooth muscle, so that way we can have the heart beating as one unified unit, and in the smooth muscle to create what's called peristaltic contractions that will help propel food through that hollow tube. We're also going to find it in a lot of embryonic tissue, in the lens of the eye, and the cornea of the eye. Here are those pictures that I promised you. So if we look at this epithelial cell, right, we've got a simple columnar epithelium, got many glyceride in the middle. And so at the bottom of that cell on the basal surface, right, we're going to have that hemidesmosome that connects the basal surface of the cell to that basement membrane, preventing that layer of epithelium from being ripped apart. Then if we look at the apical surface, or that free surface up at the top on the other side of the cell, that's where we're going to find those tight junctions. So this tight junction is going to anchor those two sides of the cell very closely together. And it has a transmembrane protein, so you can see that protein going through the cell membrane of one cell and through the cell membrane of the other cell. And it creates like this blockade. So substances cannot very easily get past that transmembrane protein. If we look at the tight junctions, these have the extensions from the cytoskeleton, creating those intermediate filaments of the cytoskeleton. And then you have the cell adhesion proteins that are found in the intercellular space that is connecting to the plaque formed from the filaments of the cytoskeleton. And then we've got those gap junctions. So typically we find the gap junctions more on the basal surface of the cell, and they make these connexin structures that are made out of the 6 transmembrane proteins with a little hole in the middle. So ions and molecules can move from one cell right into the other, kind of like this little alley or like back way or back road. like a secret door into the cells, or kind of like if you've ever had a hotel room where they've got the door connecting hotels rooms so you don't have to go into the hallway. It's kind of like those. Here we have those tight junctions zoomed in, and so you can see the intercellular space a little bit better. You can see the cell adhesion proteins that are sticking into the plasma membrane, and the desmosomes that are being created from the intermediate filaments of the cytoskeleton and connected by those cell adhesion proteins. This is a nice zoom in of the gap junction, so you can actually see that pore, how it creates like a tube in the middle of the connexon. And then that was close up of the hemidesmosome. That's going to anchor the basal surface to the basement membrane. When it comes to how this tissue grows and develops, we're going to talk about the modes of tissue growth. When I talk about stem cells, there is a difference between adult and embryonic stem cells. So we'll discuss that. And then we're also going to look at how cells or tissues can change from one cell type to another, and talk about the ways that the body repairs damaged tissue. When tissues grow, it can grow by increasing the number of the cells that are in the tissue, or it can grow by increasing the size of the existing cells. If we have growth through cell multiplication, so we're increasing the number of cells, that is called hyperplasia. Most embryonic and childhood growth is hyperplasia. You literally need more cells to get larger. Hypertrophy is where the pre-existing cells get larger. So this is what happens during exercise. When you are putting stress on your muscles and those muscle fibers, the actual fibers themselves will grow larger in diameter. We also have the accumulation of body fat. Those fat adipose cells can fill their vacuoles up and swell and become larger in size. Neoplasia is the development of a tumor that's composed of abnormal and non-functional tissue. And so neoplasia can be benign, meaning it doesn't spread, the mass just stays local, or malignant, and malignant is when that tumor will move and start growing in another portion of the body. Tissues can change types within certain limits. So for example, we have cells that are stem cells in the connective tissue, and it's all a mesenchyme stem cell, right? And as those cells develop, they are going to become more specialized to perform a specific function. So, for example, that embryonic mesenchyme stem cell can become a cartilage cell, and it will turn into a chondroblast, which will build cartilage. Or that mesenchyme stem cell can differentiate and it can turn into an osteogenic cell. Those osteogenic cells will produce osteoblasts that build bone. Metaplasia is the changing of one type of mature tissue to another. So, for example, a simple cuboidal tissue before puberty could change to a stratified squamous epithelium after puberty, or a pseudostratified columnar epithelium of the bronchi being changed to a stratified squamous epithelium for protection. Stem cells are undifferentiated cells, so they do not have a job yet, and they have the potential to be any type of cell. So they have the potential to differentiate into many types of cell types. So they are said to be totipotent, meaning they have total powers to be any cell in the body. And then as they differentiate, they will differentiate into certain germinal lines. And those are pluripotent cells, meaning they have many powers, and so they can turn into many different types of cells. So, for example, with our mesenchyme stem cells, those are pluripotent. They're going to turn into many different types of connective tissue. Right, and then eventually when they are designated to be one type of cell, that is a unipotent cell, and when it does mitosis, it will only create that type of cell. So like the osteogenic cells will only create osteoblasts. As the stem cells give rise to a diversity of mature cells, that is called developmental plasticity, right? So because we're changing the ability of what these cells can do. Here we have a morula stage of human development. So this is where a fertilized cell has started to replicate, and now we have the development of our germ layers. And we're going to see the ectoderm, stem cells. We're going to see cells start differentiating down that mesoderm and then the endoderm. Embryonic stem cells can be abbreviated as ESC. Those compose the early human embryo, right? So these cells that are from very early on in the embryo have unlimited development or developmental plasticity. So those are those totipotent stem cells, right? The cells from the inner mass, called the embryoblast of the embryo, those can develop into any cell type of the embryo, but not necessarily the organs of pregnancy like the placenta. The adult stem cells, these are undifferentiated cells that are going to be found in the mature organs. So some of these are the multipotent, and they have the ability to develop into 2 or more stem cell lines, like the bone marrow. And then some are going to be the unipotent, where they produce only one cell type. When tissue is damaged, it can be repaired in one of 2 ways. There's regeneration and fibrosis. Regeneration is the replacement of these dead or damaged cells by the same type of cell as before. So by being replaced with an identical cell, that's going to restore normal function. So for example, if you have a minor skin injury or even an injury to an organ like the liver, they can do mitosis and these cells can replace themselves. Fibrosis is the replacement of damaged cells with scar tissue. And that scar tissue is going to fill in the spaces that are too far apart or too far removed, so mitosis cannot fill those spaces in. The scar tissue will be put in instead that can hold the tissue or the organ together, but it's not going to restore the function, right? So if you have a severe cut or a burn, or if there's like tuberculosis and there's scarring of the lungs, the tissue is not going to have the same features and structures as the original, and so it's going to have an impaired function. For example, in skin wounds that are healing, when a blood vessel is severed, that severed blood vessel will bleed into the cut. There are mast cells that are present in that blood, and the damaged cells, damaged epithelial cells, will attract these mast cells, and those mast cells will release histamine. That histamine will dilate the blood vessels further and make the capillaries more permeable or able to be passed through. So the cells that make up the epithelium actually get more loosely associated, so other white blood cells or leukocytes can come into the area and start cleaning up that damaged tissue. Blood plasma seeps through that loosened capillary, and in with it comes antibodies and little clotting proteins that's going to help close the wound. There are platelets that are in the blood, and those platelets are kind of sticky. And so these sticky platelets will form a clot. And those sticky platelets are attracted to that damaged epithelium. So this is going to knit the edges of the cut together. It will make a nice barrier to inhibit the spread of pathogens, and it starts to form a scab that will temporarily seal that wound, blocking it from infection and preventing additional blood loss. The macrophages, the leukocytes that are inside of your blood, will start to phagocytose and digest any of that tissue debris, and it will start cleaning up the area. Then new capillaries will start to sprout out from nearby vessels, and deeper portions of the clot will become infiltrated by capillaries. And with that will come fibroblasts. So those fibroblasts are going to start to transform the tissue. They're going to start building new ground substance and laying down new fibers. So when we have the transformation into a soft mass, that is called granulation tissue. The macrophages will continue to remove the blood clots while the fibroblasts deposit new collagen, and that is known as the reconstructive phase. This usually begins about 3 to 4 days after the injury, but it can last up to 2 weeks. The epithelial cells around the wound, especially in that bottom layer by the basement membrane, they are going to begin to multiply, and they will migrate beneath the scab, and that epithelium will regenerate. Underneath the epithelium, any underlying connective tissue will undergo fibrosis. So scar tissue may or may not show through that epithelium. Depends on how much scarring there is. And this is known as the remodeling or maturation phase. That typically begins several weeks after the injury, and it can even last up to 2 years. When tissue starts to degenerate and die, that's where we have atrophy and necrosis. Atrophy is the shrinkage of a tissue through the loss of the cell size or number. So we can have atrophy due to aging or from the lack of use. Like if people are bedridden or people who lose the ability to walk, their legs will undergo atrophy. And when it comes to cell death, necrosis is a pathological tissue death. So this is not a normal part of the cell life. It's not normal cell death. And what causes necrosis can be from infarction, where there's a sudden loss of blood supply and blood is cut off. So that will cause sudden death of the tissue. You can have gangrene, which is due to an insufficient blood supply. So it's not fully cut off, but not enough is getting through. And so that typically that involves an infection. Oops, there's some pictures of dry gangrene. And so this is actually caused from diabetes. And you can see that black necrotic tissue, and so those cells are dead, and they're going to have to be removed. Otherwise, this necrosis can continue to spread and go to the healthy tissue. Normal cell death or programmed cell death is called apoptosis. So cells will live their life and they'll do their function and they will serve the body as many times as they can. But typically they only have about 80 life cycles, and then they have replicated too many times, and there's just too much of a risk of there being mutations in that DNA. So they will undergo programmed cell death, and they will essentially undergo cell suicide, and they will die and get out of the way. So these cells that are dying from apoptosis will be phagocytosed by macrophages and other cells, and they'll get broken down, and their cell parts will actually be reused. They'll get broken down into their carbs, proteins, fatty acids, and nucleic acids, and they will be used to build new cells and new cell parts. And every single cell has this built in to their DNA. Billions of cells die by apoptosis, and every cell has this built-in suicide program. And that brings us to our last lesson.